Okay guys, welcome to the last podcast of Unit 3. We're going to be focusing on Newton's laws of motion. Below I have our student learning objectives for this particular part of our unit. Be sure to take a look at those. Remember, those tell you what's going to be on the test. Okay, first off, Newton's first law is often written in terms of the net force. Remember, that's the overall force acting on an object, causing it to go in a certain direction. An object at rest will stay at rest, and an object in motion will continue in motion at constant velocity unless there is a net force. Remember, if we have a constant velocity, that means acceleration is 0, and our net force will also be 0. Force changes motion only when net force does not equal 0. So remember, our net forces are overall forces acting on an object. If we look at the first picture, we have a greater force here coming off of our golf club to the golf ball, whereas we have a smaller weight and normal force, and our friction is smaller than the force of the club. Therefore, the force of the club will overcome those other forces, and we'd have motion of the golf ball going to the right. So Newton's first law says that an object continue the motion they already have unless they're acted upon by a net force. So if the net force is 0, an object at rest will stay at rest. If an object is acted upon by unbalanced forces, that means its motion will then change. For example, in this first picture, this guy is just chilling and driving his car. So the forces acting upon him, so his seatbelt keeping him in place, and the forward motion of the car are balanced there. He's not moving. However, if you get in a car crash, there is a huge force acting upon you, which causes you to your car to stop and you to go forward to continue moving. So the seatbelt is counteracting the guy from moving forward after an abrupt stop. A great example would be in a car crash. Next, inertia is the property of an object that resists changes in motion. Objects with more mass have more inertia and are more resistant to the changes in their motion. So taking a look at these two different types of balls, we have a bowling ball and a golf ball. Our bowling ball has a mass of 5,000 grams and our golf ball has a mass of 50 grams. Which one has a larger mass? It is going to be our bowling ball. Therefore, our bowling ball has a higher or greater inertia. Moving on, let's go through an example here. So a car driver drives along a highway at a constant velocity. That means acceleration equals 0. Find the car's weight and the frictional force if the engine produces a force of 2,000 newtons between the tires and the road, and the normal force on the car is 12,000 newtons. So what are we looking for? We're looking for the force of weight, and we are looking for the force of friction. And what are we given? The force of the engine, which equals a positive 2,000 newtons, and we are also given the normal force, which is 12,000 newtons. The relationship between these would be since we have a constant velocity, we have 0 net force. Our solution for this, we need to draw it out. So we're going to draw out a free body diagram. So if I have my car here, and we show our F normal, so Fn, our normal force, that is positive 2,000 newtons. And we also include our force of our engine, which equals a positive 2,000 newtons. If we want to have a 0 net force, our force going up, so our force normal, must be the same as our force going down, so our force of our weight. They must be the same. However, we're going to add a negative sign because it's going in the opposite direction. And I realized, put 2,000 for both of them. We should have, oopsie, 12,000 for our normal force. And then we will have the force of our friction. That will equal 2,000 newtons as well. However, if this one's positive, so the force of the engine is positive, our force of friction must be negative to counteract that. So we would have a net force of 0 here. Moving on to Newton's second law. So Newton's first law tells us that motion cannot change without a force, without a net force. According to Newton's second law, we're just going to add on to that. The amount of acceleration depends on both the force and the mass. Acceleration is the result of unbalanced forces. A large force makes a proportional or proportionally larger acceleration. And acceleration is inversely proportional to mass. So one thing to keep in mind here, when I say a larger force makes a proportionally larger acceleration, that means my force is increasing and my acceleration is increasing. When I say acceleration is inversely proportional to mass, that means my acceleration, no, let's start out with mass first. If my mass increases, my acceleration would decrease. Here we have unbalanced forces causes changes in speed, direction, or both. So if we are having a change in speed, direction, or both, I want you to think what 3 criteria we talked about last unit we used to represent a vocabulary word. Okay, before I tell you guys the answer to that, I want to talk about net forces real quick. So here we have 2 gentlemen pushing on our box. They're both pushing to the right, so that tells me that we have a positive force here. And when we have 2 positive forces going in one direction, we add them together. So our total would be 600 newtons. And because I don't have any forces acting to the left, our net force is positive 600 newtons. Now, forces in the vertical direction. So my box is exerting a weight on the floor. So my force of my weight is going downwards. And the force from the floor is holding the box up, and that is my force in the upwards direction. That is my normal force, F normal. Or we can write an F with a capital N by it. That is my normal force. And I guess one other thing that I didn't mention when I was first talking through the problem with the 2 gentlemen pushing the box to the right, you will notice that my vector doubled in size by the end because the force is twice as great when you combine both of them together. Here, when we're going to talk about acceleration and force. So the second law says that acceleration is proportional to force. So if force is increased or decreased, acceleration will be increased or decreased by the same factor. So as force increases, acceleration increases. And the key thing is by the same factor. So if we look at our image on the side, if I double my force, I would also double my acceleration. However, if I cut my force in half, going from 1 to zero point 0.5, my acceleration would also decrease by zero point 0.5. So I'd go from 1 meters per second squared to 5 meters per second squared. So these increase and decrease at the same time, and they increase and decrease by the same factor. So if I divide one by 2, divide the other one by 2 too. Another important factor of the second law is that acceleration is always in the same direction as the net force. Oops, let's make that better. So what I mean by that is in this first image, we have a positive force. So you're hitting the gas pedal and it's propelling the car forward. We end up with a positive acceleration, and we end up with our net force. Everything is going to the right. However, in the image below, we have a negative force, so you're hitting the gas, you're slowing down. Sorry, you're hitting the brake and you're slowing down. You end up with negative acceleration. So your forces are in opposite directions. Next, if we talk about a sideways force, you'd have to turn your wheel in order to turn the car, which turns the axle in the bottom of your car, so your whole car turns. So as you're hitting the gas, you are changing directions and you get sideways acceleration, which would be centripetal acceleration. Now we're going to talk about acceleration and mass. So the greater the mass, the smaller the acceleration for a given force. This means acceleration is inversely proportional to mass. That means as mass increases, acceleration would decrease, or if we say as mass decreases, acceleration would increase. We can see that here we have this gentleman pushing this cart. It's a very small mass. Therefore, his acceleration is greater than over on the right. He has much more mass, and his acceleration is really tiny. The vector is much smaller to represent that. Okay, so applying the second law, we need to keep a couple things in mind. The net force is what causes the acceleration. If there is no acceleration, the net force must be 0. And if there is acceleration, there must also be a net force. Remember here that our forces would be unbalanced. Lastly, the force unit of newtons is based on kilograms, meters, and seconds. So we can interchange some of those units, and I'll go over that in a minute. Now on the right, I have our equation. Force equals mass times acceleration manipulated a couple times. So you guys can see if you're solving for acceleration, you have force over mass, or if you're solving for mass, it is force over acceleration. So feel free to use that. We can also use our triangle here. We'd have force on top, acceleration, and mass on the bottom. Remember, you just cover one up, and the two that are remaining, they're above each other, or on the same plane as each other. You're multiplying, they're one over another, you're dividing. So let's go through an example here. A car has a mass of 1,000 kilograms. If a net force of 2,000 newtons is exerted on the car, what is its acceleration? So what are we looking for? We're looking for its acceleration. What are we given? A mass of 1,000 kilograms. And we are also given a force of 2,000 newtons. The relationships between all of these, so equation force equals mass times acceleration. However, since we're solving for acceleration, we would manipulate our equation and we would have acceleration over, or acceleration equals force over mass. Last thing we do for our solution is plug our numbers in. I have a force of 2,000 newtons. I put that over my 1,000 kilogram mass. I will end up with 2 newtons per kilogram for my answer. I want you to realize this newtons per kilogram. You can also say it's meters per second squared. They mean the same thing. Okay, third law. Almost there, guys. So here we have two forces acting on one another, and we have, so for every action there's an equal and opposite reaction. We have Isaac Newton here pushing on an elephant. They're both on a skateboard. When they push off, we will see that Sir Isaac Newton has a much larger acceleration because his mass is smaller, where the mass of our elephant is larger. So that means his acceleration will be smaller. His acceleration here is larger. Okay, here we have Newton's third law states that every action force creates a reaction equal in strength and opposite in direction. One thing I want you to pick out about this word strength, it also can mean magnitude. I know when I was talking with vectors originally, I talked about a vector has both magnitude and direction. And magnitude is how large your force is. So strength, how large your force is. Same meaning here. There can never be a single force alone without its action-reaction partner. For example, in the first image, if we are throwing a ball, our action would be for the ball to go forward from our hand, and we would feel that force of the ball leaving our hand. That would be the opposite reaction. And then if the ball's coming back towards our hand, the reaction is going from the ball to the hand, and then we'd feel that impact upon our hand. So it would hit our hand, and then the reaction would be the force back on the ball once we've stopped its motion. So some guidelines for action-reaction forces. Both are always there whenever any force appears. You guys may not think of it this way, but when you're walking on the ground, when your foot pushes down, that's your action, and the reaction is the floor pushing back up on your foot. They always have the exact same strength, so action, reaction are always equal in magnitude, remember, so our arrows will be the same size, but in opposite directions. They always act in opposite directions, so make sure when you draw your arrows for an action-reaction, you have one going in either direction. If you don't, you know that something's wrong. They always act on different objects. So my foot in the ground, I have one acting down from my foot to the ground and one acting up from the ground to my foot. Both are real forces and can cause changes in motion. I can push off of the ground with a force. So that's what I'm doing right here. So the force I push down on the ground with is equal to the force that the ground's pushing back up on me. But if I'm on a skateboard, I can change my motion. I can start rolling down the sidewalk. Another example here for you guys. So a woman with a weight of 500 newtons is sitting on a chair. Describe one action-reaction pair of forces in this situation. So what am I looking for? I'm looking for an action-reaction. Means I have to have arrows going in opposite directions. What am I given? I'm given the force of her weight, which is 500 newtons, and she's sitting down on a chair. So here we're going to talk about forces being up and down, so vertical direction. So if it's going down, we're going to have a negative 500 newtons there. And then the relationship, we have equal but opposite. Now, our solution, we would have to draw a free body diagram. So if I draw my chair here, the woman, her force is downwards, so her force of weight equals negative 500 newtons. To counteract that, we must have a force that's going from the ground back up with the same, remember, strength, so our vector will be the same size, and that's our normal force because it's coming from our surface. We're going to have a positive 500 newtons here. Because remember, equal but opposite. So negative 500 and positive 500, equal and opposite there. And remember, our normal force, this is our reaction. Her sitting is our action. Now let's talk about momentum. Newton's third law tells us that any time two objects collide, they exert equal and opposite forces on each other. Momentum is the mass of an object times its velocity. The unit for momentum are kilograms meters per second. So we can also take it to kilograms times meters per second. This whole thing, written either way, they are a whole unit. I need to see all of it when we're talking about momentum. Momentum, we use a P to denote it, and then we have mass and velocity with C. So let's go through this example here. I'm going to go through the first one with you guys, and then you guys can do the second and third. So our first one, second, third. You guys can do the second and third, and then come and check your work with me. For the first one, we're going to calculate the momentum of a 1,200 kilogram car with a velocity of 25 meters per second. So what are we looking for? We're looking for momentum. What are we given? We are given the mass of our car, which is 1,200 kilograms, and we are given our velocity, which is 25 meters per second. The relationship between all this is our equation for momentum. Momentum equals mass times velocity. Our solution would be plugging our numbers in. So we'd have 1,200 kilograms times my 25 meters per second. My momentum would end up being 30,000 kilograms meter per second. You can see that none of my units cancel off, so they are both present in my answer. Now you guys try number 2 and 3, and you can come back and check your answer. So I have the answers here squared off in purple. If you have any questions, please come in and talk to me, and we will straighten it all out. Now let's talk about the law of conservation of momentum. It states that as long as the interacting objects are not influenced by outside forces like friction, the total amount of momentum is constant or does not change. So assuming that there is no friction when this boy throws the ball, since he's throwing it to the left, we have a negative sign there for our force. He will move in the opposite direction, so to the right, which would be a positive velocity, assuming there's no friction, and they would both keep moving forever. Let's put some numbers with this so we can actually see how this happens. So the results of a skateboarder throwing a 1 kilogram ball at the speed of negative 20 meters per second is that he and the skateboard with a total mass of 40 kilograms move backward at a speed of 0.5 meters per second. If we ignore friction, key thing there. So let's split this up. We have momentum equals mass times velocity. The equation is the same for both sides. Now, if we just want to talk about the ball, our ball is 1 kilogram. We're going to multiply it by the velocity, which is negative 20 meters per second. So our momentum would equal negative 20 meters per second. Now, if we took the information for the boy, we would see that he has a mass of 40 kilograms, and we're going to multiply that by his velocity, which is positive 0.5 meters per second. We end up with a positive 20 meters per second for his momentum. As you can see, our momentums are the same, but they're opposite. Okay, last slide, guys. So if we had an astronaut and he was stranded in space and he's trying to get back to the space station. So in this scenario, we'd have extremely reduced friction. And the only thing he has with him is a wrench. If he throws a 2 kilogram wrench at a speed of 10 meters per second, the astronaut would move backwards at a speed that could enable him to reach the space station again. And the astronaut's mass is 100 kilograms. Let's go through how to figure out how to get this guy home. So what are we looking for? We're looking for the velocity of our astronaut. So I'm going to do V and A for that. Don't know what that is. What are we given? We're given the velocity of our wrench. I'm going to use a W for that. And the velocity of the wrench is positive 10 meters per second. Sorry, I mean negative 10 meters per second because the wrench is going to the left. Next, we have the mass of the wrench, which is 2 kilograms. And we also have the mass of our astronaut, which is 100 kilograms. What is the relationship between these? Well, we're going to be using an equation for momentum equals mass times volume. And what we can do is we can take our momentum of our astronaut equals our mass of our astronaut times our velocity of our astronaut. And we take the momentum of our wrench equals the mass of our wrench times the velocity of the wrench. Because we have equal but opposite reactions, that tells me I can set my momentum of my astronaut equal to my momentum of my wrench. And we can take these parts and set them equal to one another. So I have my mass, my astronaut, times my velocity of my astronaut equals my mass of my wrench times my velocity of my wrench. Last thing here is I'd plug in my numbers and I'd solve for my missing piece, which is my velocity of my astronaut here. So the mass of my astronaut is 100 kilograms times the velocity of my astronaut equals the mass of my wrench, which is 2 kilograms, times the velocity of my wrench, which is negative 10 meters per second. Now what I would do to get my velocity of my astronaut all by itself is I divide each side by 100 kilograms. That would cancel out there. My units for kilogram would cancel out. And I would end up with, I'm going to write it on the side because I ran out of room there, the velocity of my astronaut would be 0.2 meters per second. One last thing, I hope you don't feel like I'm ignoring my negative sign here for my negative 10 meters per second. Technically, I would get a negative 0.2 meters per second. However, if we're going in the opposite direction, so my astronaut is accelerating in the opposite direction, um, or moving, I should say, because it's his velocity, he would have a positive acceleration. If one of my acceleration, I keep saying acceleration, I'm sorry, if one of my velocities is positive, negative, so my starting velocity, then my ending velocity, so my unknown would have to be positive. So that's why I didn't include that. So sorry if that caused any confusion. If you have any questions, bring them to class and we'll answer them.